Hello everyone, my name is Antoine André. I am part of the Femto-ST Institute located in France, and I will present you a computer vision method to retrieve nanometric displacement over a large centimetric range. This article is entitled Sensing 1 nanometer over 10 centimeters, a micro-encoded target for visual in-plane position measurement. To introduce this work, we can take a look at the GPS method that has a resolution of positioning below 1 meter all over the Earth. Therefore, this positioning method has a 10^8 range to resolution ratio. What if, instead of Earth, we have a ping-pong ball and a positioning method with the same range to resolution ratio as the GPS? With this, a positioning method applied to a ping-pong ball will be able to sense displacements around 1 nanometer. This article presents a method with a 10^8 range to resolution ratio and a 10 by 10 centimeter target with a 1 nanometer resolution in translation and a 4 microradians resolution in rotation. This work is motivated by the need of more powerful tools to calibrate 1 to 3 degrees of freedom stages over large areas or to precisely calibrate actuators. With this method, accurate real-time visual servoing over a large range is also possible. Finally, this work allows one to enhance large positioning systems by placing an absolute and accurate internal sensor. With this done, we can now take a closer look at the process of the target conception. The presented target uses the properties of a periodic pattern to retrieve an accurate position based on the phase of the pattern. So firstly, we place a one-dimensional periodic pattern on our target. Since the target is meant to be absolute, we add an absolute binary sequence over the periodic pattern. In order to keep as much periodic information as possible, each coding byte of the sequence is padded to the right and to the left with an always present fringe. Since the presented target is bidimensional, we take the first direction encoded pattern and cross it in the other direction. By merging the two directions with a logical end product, we obtain a two-dimensional periodic encoded pattern. Finally, in order to remove the orientation ambiguity, we remove one of the always present dots that was the result from the byte padding of the encoded sequence. This process results in the creation of multiple 3x3 cells that always present the same shape, with an absent dot which is used for the orientation keying, 3 always present dots which are used to enhance the periodicity of the pattern, 2 dots in each direction which give the coding information coming from the encoding sequences, and 1 dot which is the result of the product of the 2 other coding direction dots. Once the target is printed on a wafer of 10 by 10 centimeters with a physical period of 9 micrometers and placed in front of a microscopic objective, we can acquire images of small parts of the overall pattern. In order to retrieve both the nanometric position and the global position of the pattern image in the whole encoded target, we need to take several steps. First one is to take the Fourier transform of the pattern image that gives us, by isolating the two main frequency peaks and taking the inverse Fourier transform, the phase evolution between -π and π for each direction. With these two phase maps, we can reconstruct both the outside of each dot of the pattern by selecting the phase around π and the phase around -π in each direction. Similarly, by selecting the phase that is around 0 in each direction, we can isolate the center of each dot. These two reconstructed patterns allow us to apply a threshold on each dot of the original pattern image, leading to an accurate and robust local threshold binarization, which presents the bidirectional encoding binary sequence. By searching with the convolution product the position of these subsequences inside the whole encoding sequence in both directions, we can find the rough position of the pattern image in the pattern referential. Finally, by combining the fine phase information that gives us a pose with a nanometric resolution in translation and a micro-radian angular resolution, with the rough encoded position, we can retrieve the pose of the acquired pattern image in the whole 10 by 10 cm pattern referential. This method was tested with different experiments that showed nanometric resolution over a large range of displacements. As presented in this table, the static performances of the method are below 1 nanometer in both directions, and the angular resolution is proved to be around 4 microradians. The method was also tested with a nanometric stage and proved to be able to retrieve square signals of 1 nanometer sent to the actuator. To ensure the method was accurate, a linearity test was also conducted both in translation and rotation. Results are also presented in this table. Finally, a test conducted with a more macroscopic robot allowed us to validate the large range position retrieving. Recent experiments focusing on the robustness of the method showed that the method was able to perform even in defocused conditions, this way enhancing the depth of field for image acquisition. Other experiments on occlusion, noise, and uneven lighting showed that the method was robust to different kinds of poor imaging conditions. With this robustness and the nanometric positioning performances, the method can be implemented on nearly any system, even with bad image acquisition conditions. To summarize the main advantages of the method and to conclude this presentation, presented method is a 3 degrees of freedom, easy to implement, large range to resolution sensor. The fact that the measure is reported outside of the positioning stage allows to diminish errors caused by complicated conception of inserting multiple internal sensors inside the system, such as multiple interferometers, for example. The large range to resolution ratio of the method allows different applications such as large-scale and accurate nanometric visual servoing, or can be used to calibrate up to 3 degrees of freedom stages. Finally, the robustness of the method allows to implement the setup even in poorly favorable imaging conditions. Thank you for your attention. Further details about this presentation are given in the corresponding transaction on Mechatronics article.